Okay, I hope you had a chance to look at this problem. Basically what I asked you to do is make a plot of the output voltage versus input voltage for that previous circuit. And this is referred to as a transfer characteristic. Well, look, what we have to do here is really look at the three different cases and put that information onto this graph. So look, case number one. Vin equals 0.7, the output VO was 0. That was the onset of conduction. So let's put that information over here. So if we do that, not the scale, but look, there is my Vin 0.7, and of course the output voltage being 0. Case 2, when Vin is greater than 0.7, the output is really equal to the input minus 0.7. All right, let's take an example here. Supposing Vin reaches 10 volts, as in the previous problem. Then the output would reach what? 9.3. So we could plot that information on there. We could say there's 10. We could come up here and let's say that that was the 9.3, and it was simply determine that point. There it is, and then we can draw a line between those 2 points, and that's the relationship then of this output versus this input when Vin is greater than that 0.7. Case number 3, Vin is less than 0.7, the output then is equal to 0, and so really we have our curve running along this horizontal axis like so. And so then this represents the transfer characteristic for that particular circuit. All right, what I want to do now is, before we leave this particular problem, is look at what might happen. So this is our previous problem. I want to look at what might happen if I were to come along and, let us say, take a capacitor and basically connect it like so. And here, of course, is the output voltage, VO plus minus. Now here is our previous problem. This is what we found for the output as a function of time, really. So we found that the output would rise up to 9.3 volts. That occurred when Vin was 10. All right, let's consider that case. Vin has reached 10. This output over here has reached this 9.3 volts. So we're looking at, if you like, this point in time right here. Okay. Well, this capacitor is really going to hold this voltage at 9.3. So even when Vin starts to now fall, as we move on in time, this output voltage is going to basically be held by this capacitor. The capacitor has to discharge for this voltage to fall. Now, the capacitor cannot discharge through the diode. The diode cannot conduct current in that direction. It can, however, discharge through this resistor. But if we were to make, if you like, this capacitor-resistor combination very large, it would take a very long time to discharge. And so what we might see is really a waveform that would look like this. The capacitor then charges up to 9.3. Okay, Vn starts to fall. The capacitor then tries to discharge then through this resistor, but it's doing it very, very, very slowly because of the large value, if you like, of the CR combination. Then, of course, it reaches this point here. At this time, Vn, of course, is increasing, recharging that capacitor back up to 9.3 volts. And so what we end up seeing then is a waveform that sort of looks like this. Okay, looks pretty flat. You could say, well, there's a bit of a ripple there. The size of that ripple then is going to be a function of basically the size of the CR combination here. And the larger that is, the less ripple that we'll effectively have. And so what we're seeing here is we're seeing a DC type of voltage being produced by that capacitor. And that capacitor is often referred to as a smoothing capacitor. Okay. One of your lab problems actually gets you to look at a circuit like this in more detail. All right, now what I'd like to do is consider in this block, I'd like to consider another clipper example. All right, the example that we'll consider is the following. All right, we're going to take, again, a little sinusoidal voltage source. We'll call that once again V in plus, and we'll say that it has a peak value, like before, of 10 volts. We're going to put a resistor here this time, and then we're going to put the diode in this position here, and we're also going to put a voltage source, and we're going to make the voltage source 5 volts, and this is the circuit now that we're going to try to actually deal with, and we're going to look at this output voltage VO as a function really of that input voltage. Let's define the voltage across the diode, plus minus VD. All right, now it's a methodology that we're really trying to develop here, a way to approach these problems, okay? So what we'll do is we'll look at case 1, okay, and we'll say case 1 is really the onset of conduction, all right? At the onset of conduction, the voltage across the diode reaches 0.7, but the current through the diode is still at 0, okay? And if you looked at your characteristic here, this is ID versus VD. Basically what we're saying is that we're at this point right here, okay? All right, what are we going to do next? Oh, guess what? We're going to take a loop, all right? So we'll go around the loop. Here we go around the loop. So we'll go from a minus to a plus. We say that is V in. Now the voltage across that resistor, since this current is 0, of course would be 0. So I'll put a minus 0 there. Then we've got a drop, minus VD, and then we've got another drop, minus 5, all equals 0. Okay, let's now put in this value of VD, which is 0.7. So really what we've got is V in minus 0.7 minus 5, all equals 0. So in other words, the question is, how big did I have to make this V in to bring me to the onset of conduction? Well, that's easy now. Take these two terms to the other side, and we have V in being equal to 5.7 volts. Okay? So that's the value that we had to bring V in to bring us to the onset of conduction. Last question for this case is, well, what is the output voltage? VO. Well, this may be very obvious because here is VO between here and here. You've got 5 here, you've got 0.7 here, and you could very quickly argue that VO would be 5.7 volts. Okay? And so that's the VO. If you were in doubt, you could go ahead, as I've said before, just take a loop, and if you went round the loop, let's say do that very quickly, we'd have what? We'd have a 5, and then we'd have a minus to a plus, so we'd have a plus VD, and then what? Plus to a minus, minus VO, all equals 0. And so we could say what? VD is 0.7, VO could be taken to the other side, so we have 5.7 is simply equal to VO. All right? And so that is the first case for onset of conduction. All right, there. V in brought to 5.7, output voltage being 5.7. All right, next, case 2. All right, let's look at V in now, okay, greater than 5.7. And in this case, what are we saying? The diode basically is conducting. So the diode is conducting. In the conducting case, we can say VD is 0.7. The current ID, clearly though, is not equal to 0. Okay, so let's just redraw the circuit again. Here is our circuit. Here is V in. We've got our resistor sitting here. And then, of course, we've got our diode sitting here. Our voltage source like so. All right. Now, we're looking at when V in here is greater than 5.7, what is this output voltage going to be? All right, well, the diode is conducting, so really, across that diode, I have VD. VD would be what? 0.7. And so therefore, I think very clearly you can see here that the output then is VD plus this voltage here, which was 5. So the output basically becomes, or stays, at 5.7 volts. Okay? So if we increase V in above 5.7, this output remains fixed. Once that diode is conducting, the voltage across it remains fixed at this 0.7 volt value. So that is the case then, case 2, when the diode is conducting. Okay? All right, now let's look at the final case, which would be case 3. All right. and we'll say that the diode is not conducting, or we'll say the diode is off. It's like an open switch. All right, let's just look at the circuit once again. Here is our circuit, V in. Here is the resistor. Here's the diode. And here is my voltage source. 5 volts plus minus the voltage across the diode. Okay, and I'm trying to find now the relationship of this output voltage to the input voltage. Okay, diode is off. Well, look, in this particular problem, very quickly, we could take a loop that would incorporate V in and would incorporate VO. Look, one loop that we can take is really this loop here. If I were to go around that loop and start here, what have I got? I've got V in, okay? The voltage across that resistor, what is it? Well, if the diode is off, the current ID must be equal to 0, okay? So there's no drop across the resistor, okay? So we'll say minus 0 volts because there's no drop across it. And then we come from here to here. What is that? That's a minus VO, all equals 0. And so therefore, take the VO to the other side. We have V in is basically equal to VO, or VO is equal to the input voltage for that case. What is that case? That is the case basically where V in is less than 5.7 volts. The diode is in an off condition. Now look, a little exercise for you, all right? You can think about this, all right? So, little problem for you. Supposing I said to you that V in was equal to a minus 10 volts, okay? Could you find the voltage across the diode, VD, and then could you check, okay, that really the output is still the same as the input for that condition? So that's a little problem I'd like you to go away and think about. Basically, it's a very easy little problem. You can do it by way of loops, and just have a look at that. Remember, the diode is off in that particular case. All right, diode off, current in the circuit is 0. We're looking at the condition where V in is a minus 10. All right, the final thing that we need to do here then is to really take that information and then look at basically that output waveform and maybe that input waveform. So what I'll do over here is I'll write down the cases and summarize. Case number 1, okay? We found onset of conduction, V in had to be brought to what? 5.7 volts. The output was 5.7 volts. That was our first case. Then we had what? Case number 2. And we said if we make V in greater than what? 5.7 volts, the output basically remained fixed at 5.7 volts. And then case number 3, okay? And we said here that supposing V in is less than 5.7, what is the output? The output is really the same as the input for that particular case. So let's see if we can draw this. Once again, my drawing here is not going to be particularly accurate, but hopefully it will give you the idea. All right? So here, if you like, is my input voltage looking something, if you like this. This is reaching 10 volts peak, and if you like, minus 10 volts. Okay, this is a plot of V in versus time. All right, let's look at the output over here. So this is the output versus time. If you like, this is VO. All right, what have we got here then? Well, let's look and plot on this graph the points where the onset of conduction begins. That's V in 5.7. All right, so let's imagine that's hard to write in, but 5.7. That's the onset of conduction points that I'm just showing across this graph like so. Okay, let's bring that information down to the output graph, bringing down to the output graph like so. All right. All right, now let's look at the next case. When V in is greater than 5.7, that's here and here, what's happening to the output? Well, it remains fixed. At what value? 5.7. So that remains fixed at 5.7, fixed at 5.7. So there is that at 5.7. Case number 3, when V in is less than 5.7, that must be all of this and all of this, right? And this, the output is equal to the input. And so really, in this region, the output is simply following the input like so and like so. And there we have our plot of output voltage as a function of time. And basically, what have we done with this circuit? We've just really clipped off the top part. Okay? Now, one other thing I'd like you to do, see if you can plot the transfer characteristic for this.